All right, today in Algebra 2, we're going to do day 1 of 3.1, graphing polynomial functions. Our central question, what can the rule for a polynomial function reveal about its graph? And what can the graphs of polynomial functions reveal about the solutions of polynomial equations? How do the key features of a polynomial function help you sketch its graph? After this, you should be able to predict the behavior of polynomial functions. So first, let's get some vocabulary out of the way. So how do we classify polynomials? A monomial is a number, variable, or a product of a number and variable. And so an example of this is like x or 2x. Okay? So monomial, just one. Polynomial, a monomial or a sum of monomials. So an example, you could have x squared plus 3x minus 10. Poly just means many. A polynomial function has this form, right? So a sub n to x to the n power plus a sub n minus 1, x to the n minus 1. It just means that your highest exponent will go first. That is standard form. Exponents must all be whole numbers, and coefficients must all be real numbers in order for it to be a polynomial. Standard form, again, like we just said, all the terms are written in descending order of exponents from left to right. The leading coefficient refers to the non-zero factor that is multiplied by the greatest power of x. The degree of the polynomial is the greatest degree of any of the terms. Up to 5, okay, fifth degrees have special names. So if it has a degree of 0, it is known as just a constant. This is just any number. So an example would be like the number 10. That is a 0-degree polynomial, known as just a constant because there's no variable. If it's a first degree, it's a linear. So an example would be like x plus 3. A second degree polynomial is referred to as a quadratic. An example, x squared plus 6x minus 8. A third degree is called a cubic. So an example could be x cubed minus 2x plus 10. A fourth degree is known as a quartic. So we could say x to the fourth minus 2x squared plus 1. And a quintic is a fifth degree. So let's say x to the fifth plus 6. Okay. So we're going to start out nice and easy. Write each polynomial in standard form. Identify the degree, the leading coefficient, and the number of terms. Okay? So number 1, 2x minus 3x to the fourth plus 6 minus 5x cubed. So my highest exponent is the 4. So standard form says negative 3x to the fourth. My next exponent down is the x cubed, so minus 5x cubed. Plus 2x plus 6. So that's standard form. The degree, it's a fourth degree. Fourth degree has a special name. That is a quartic. And the leading coefficient, LC, that's the number out in front of the highest exponent. So negative 3 in this case. And it has 1, 2, 3, 4 terms. Okay. Number 2, x to the fifth plus 2x to the sixth minus 3x to the fourth minus 8x plus 4x cubed. So first we're going to put it in standard form, highest exponent, and then going descending order. So 2x to the sixth plus x to the fifth minus 3x to the fourth plus 4x cubed minus 8x. There is our standard form. It is a sixth degree. 6 does not have any special names. Our leading coefficient is a 2, and we have 1, 2, 3, 4, 5 terms. All right, a polynomial function is a function whose rule is a polynomial. End behavior of a function's graph is the behavior of the graph as x approaches positive infinity or negative infinity. The end behavior is determined by the function's degree and the sign of the leading coefficient. So let's look at the chart on the back. If the degree is odd and the leading coefficient is positive, our end behavior as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches infinity, which is just a fancy way of saying that it goes down and then up. An example of this might be something that looks like this. So from left to right is how we read a graph. Oh, I just drew that backwards. Sorry. Let's try that again. So here's my graph. I want to look at this. So this would be an example of the graph. So from left to right, the graph here is going down, and then on the right hand side it's going up. So as x is approaching negative infinity, as my x's are going this way, my graph y, f of x, is approaching negative infinity. As my x is going this way, or approaching positive infinity, my y's, or my f of x's, are getting bigger, approaching positive infinity. If my degree is odd, right, and so these we're talking about like x cubed, x to the 5th, x to the 7th, this is what we're talking about, okay? And so here my positive coefficient, so I would have had like 2x cubed. Right? Negative coefficient, I'm looking at like negative 2x cubed. Okay? So this is just the opposite of the one above it. So here, as x approaches negative infinity, f of x approaches positive infinity. So my y's just change. As x is approaching infinity, my y's approach negative infinity. That's just a fancy way of saying up, down. So the graph might look something like this, the first one that I was drawing. So like this. So as my x's are getting smaller, my y's are getting bigger. As my x's are getting bigger this way, my y's are getting smaller. Okay. Now we're going to look at if the degree is even. So this is like x squared, x to the 4th, x to the 6th, and it's positive, so like positive 2x squared. So x is approaching negative infinity. F of x approaches infinity. As x is approaching infinity, f of x approaches infinity as well. This is just a fancy way of saying up, up. So this is like y equals x squared, right? We know a parabola, if it's a positive number, it's a parabola that opens up. So as my x's are getting smaller, my y's are getting bigger. As my x's are getting bigger, my y's are also getting bigger. And then the last one, if my degree is even, so again, x squared, x to the 4th, x to the 6th, and it's a negative leading coefficient, so like negative x squared, and it takes the one above it, and it just changes the y's. So as x approaches negative infinity, f of x also approaches negative infinity. As x approaches positive infinity, f of x approaches negative infinity. And again, it's the one above it, the opposite of everything. So instead of up, up, this is down, down. And we know that if we were going to graph the parabola, y equals negative x squared, it's a parabola opening down. So my end behavior, down, down. As my x's are getting smaller, my y's are getting smaller. As my x's are getting bigger, my y's are getting smaller. All right, so we're going to determine the end behavior of the polynomial using the leading coefficient and the degree. Okay? So number one, this is the polynomial that they gave to me. So we want to look at what is the highest degree. The highest exponent is a 6, so that's even. My leading coefficient is positive 2, so even and positive. My end behavior is up and up. Number two, my highest degree is 3, so that's an odd number. My leading coefficient is negative 5, so negative. So odd and negative is down, up. Number 3, my highest exponent is a 5, so that again is an odd number. My leading coefficient would be that positive 12. So odd and positive is up, down. And number 4, my highest exponent is 4, so that's 4 is an even number, so my exponent is even. The coefficient in front of that is -4, so that's negative, so even and negative, down and down. All right, so next we're going to talk about graphing a polynomial function from a table of values. So points where the function values change from increasing to decreasing or decreasing to increasing are called turning points. To find this should say possible number, so to find the possible number of turning points, you can take the degree of the polynomial -1. And so we just say n is the degree. And so then n minus 1 tells you how many turning points you would have. A point where the function has the least value over an interval is called a relative minimum. The point where the function has the greatest value over an interval is a relative maximum. We will always sketch a polynomial graph with smooth curves, no sharp edges here, okay? All right, so use a table of values to identify key features and sketch a graph, okay? We're also going to use a graphing calculator in class to help identify zeros and turning points. To help identify zeros and turning points. So number 1, f of x equals -1/2 x to the 4th plus 3x squared plus 2. I can look at possible turning points. My highest exponent is a 4, so 4 minus 1 is 3. So this graph could have at most 3 turning points. So we want to identify the intervals where the function is increasing and decreasing. We're going to do a table of values from -3 to +3. To find f of x, we plug -3 in for all of the x's. Or since we have access to graphing calculator in class, we will type in -1/2 x to the 4th plus 3x squared plus 2 in the y equals, like we're going to graph it. And then we're going to go to the table feature, and the graphing calculator is going to fill in all this for us. So the -3 to 3, so at -3, the f of x is -11.5. At -2, it's 6. -1 is 4.5. At 0, we're at 2. Then we're back to 4.5. 4.5. Sorry about that. 6 and -11.5. So if we look at our table, before we've even graph it on the graphing calculator, if we look at our table, we can see our y's are -11.5 and then 6. So right there is increasing. And then from 6 we go to 4.5 and then to 2. Okay? So we can see that here we are decreasing. And then from 2 we go up to 4.5 and up to 6. So we can see that we are increasing again. And then from 6 we go to -11.5, so decreasing again. All right, if we were to graph this, right, I'm going to just plot these points that we have over here. So 0, 2, 1, 4.5, -1, 4.5. 2 is at 6. -2 is also at 6. And then -3 was at -11.5. +3 as well. And we can see then that we're going to connect the dots. We always connect our dots from left to right. So I start down here, and then I have to get to this next one up here, 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 there, and then back down. So our graph would look something like this. Again, I could check my end behavior. I see that I have an even degree and a negative, so I know that my end behavior was going to be down, down. which we see down and down. We graph it on the graphing calculator. Okay? Once we already have this in y equals, if you hit graph, you'll see that you get something very similar. So now let's go ahead and identify our intervals where we are increasing. From left to right, I see that if I start down here at negative infinity, and remember that when we are talking increasing, decreasing intervals, we're always talking about x values. So my x values are negative infinity, and I stop increasing right here. So that was at -2. So I'm increasing from negative infinity to -2. And then my graph at this point coming up starts to increase again. And so that is from 0 to this point, which was +2, which is exactly what we showed over here, right? We said we stopped increasing at -2, and then we started increasing again. We picked back up at 0 and increased again to 2 over here. So now decreasing, if I look at my graph, this part right here of my graph is decreasing. It's going down. That is from -2 to 0. And then from this part all the way down is decreasing again. That is from 2 to infinity. And again, that's what we had over here. So we said we were decreasing from -2 to 0, and then decreasing again from 2 on to infinity. So then we talked about the relative maxes and mins. So we're going to pull these out. So this graph has a relative minimum, and those are going to occur at your turning points. Okay, so our graph, let's see, we come up, we change directions. So that's 1 turning point. We change directions 2 and 3. So this graph does in fact have 3 turning points. We notice right here we have a relative minimum. Okay. So at turning point, that's the low point. So we have a relative minimum at the point 0, 2. This graph has 2 relative maximums, right, here and here. So relative max, we have 2 of them on this graph, and they occur at the points -2, 6 and 2, 6. So your relative mins and maxes will occur at turning points on your graph. Okay? All right, so then it says, let's use the graph to estimate the average rate of change over the interval -2 to 0. Remember, we've done average rate of change before. Our formula says we take f of b minus f of a, all that divided by b minus a. So basically it's y2 minus y1 over x2 minus x1. So if we take x2 is 0, I need to look at my graph. When x is 0, what was my y? My y was 2. So I have 2 minus, now I go to my x, -2. When x was -2, what was my y? -6, divided by those x values, 0 minus -2. So I get 2 minus 6, -4. 0 minus -2 turns to +2, so -2. The average rate of change over that interval is -2. All right, let's do one more of those. Identify key features, graph, and find the average rate of change of the interval 0 to 2. So first, I can look at my highest degree is 5, so that's odd. My leading coefficient is positive. So odd and positive, I know my end behavior is going to be a down-up. Okay. I could have, let's see, 5 minus 1. I could have at most 4 turning points. We're going to do our table, x and f of x. We're going to do the same numbers, -3, -2, -1, 0, 1, 2, and 3. And again, we're going to type this into our graphing calculator underneath the y equals. And then we're going to go to the table function. And we're going to find out that this is -110. This is 21, 8, 1, 30, 125, and 436. All right, so let's graph these. Okay, so 0, 1, that's an easy one to put on our graph. -1, 8. Negative 221, so somewhere up here. Negative 3, negative 110. So somewhere way down here at negative 3. 130, somewhere way up there, and then they just keep getting bigger. And again, I know that my end behavior, so down, okay, starting at the furthest most point to the left, and then I have to go to this point, this one, and then back up. Okay. And again, if we look at our graphing calculator, we will plot it on the graphing calculator so we can see. And we see that we're going up, come here, we turn, and if you notice on the graph on the graphing calculator, it comes to about right here and turns and goes back up. And so this graph actually has two turning points, one up here and one down here. You can identify where it is increasing. Okay. So the intervals where it's increasing. So from left to right, I'm starting down here and I'm going up, 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 up until that point. So I'm increasing from negative infinity until negative 2. And then at this point, I'm going up again. And so about 0 to infinity. Where we are decreasing. So decreasing, we are decreasing from here to here. And so that is about negative 2 to 0. Okay. All right, let's look at our relative max. So our relative maximum is at this point right here, which is the point negative 221. We can use our calculator to get our relative min. Our relative minimum is at this point right here, which on your calculator, it tells you that that is approximately at negative 0.13, 0. Now we're going to do the average rate of change. The interval 2 to 0, so when x is 2, my y value was 125. Minus when x was 0, my y value is 1 over 2 minus 0. So I get 124 divided by 2, which is 62, is the average rate of change over that interval. All right, that's where we're going to stop at for day number 1 of section 3.1, graphing polynomial functions.